All right, brothers, let's jump right into it. Today, we're unpacking a critical standard operating procedure for the plant, Incident 23. As wastewater operators, we all know our UV disinfection system is literally our final line of defense before treated water hits the natural environment. When that system loses power, we've got a massive emergency on our hands. So grab your notebooks because we're going to break down exactly how to diagnose and resolve a UV lamp power reduction safely and effectively.
We've got a solid 6-step game plan for this explainer. We'll start with a quick refresher on UV basics, define exactly what a power drop entails, show you how to spot the warning signs on the floor, run through our 7 root cause checks, take corrective action, and finally, lock down our monitoring so this doesn't happen again.
Okay, part 1. Let's talk UV technology basics. Like I said, this is our final line of defense.
You guys already know our systems use low-pressure or amalgam mercury lamps, and they emit UVC radiation at exactly 254 nanometers. That specific wavelength, it's our bug killer. It physically destroys the DNA and RNA of bacteria and viruses so they can't multiply. But to actually get that kill rate, we absolutely have to respect the 3 golden rules of UV treatment. First, the UV dose. Second, the UV transmittance, or UVT%. And third, the contact time in seconds. If even one of these fails, the whole system collapses.
Take a look at this target number, 20 to 40 millijoules per square centimeter. That right there is our standard design dose to wipe out E. coli and coliforms. If our UV power drops and we fall below that threshold, the bugs survive. And if the bugs survive, we are instantly failing our discharge permits.
That brings us to part 2, Incident 23. This is what happens when the lights literally go dim.
So what exactly is Incident 23? The official SOP defines it as a reduction in UVC emission power leading to an insufficient UV dose. In plain English, it means E. coli and total coliform concentrations are spiking way past our biological discharge limits. A low UV intensity alarm is going to trigger, and suddenly we are completely out of compliance.
This isn't just a minor hiccup. This is a massive emergency for the plant. Violating biological discharge standards means we're looking at heavy fines and a potential shutdown. We have a mandatory obligation to halt discharge to receiving waters immediately. If we don't, we're risking spreading dangerous biohazards right into our local rivers, which impacts downstream public health. Plus, think about the efficiency side. We're literally wasting electrical costs running lamps that aren't even doing their job.
Moving into part 3. Identifying the warning signs. Let's talk about how to read the symptoms out there.
First up, your systemic red flags. If the lab comes back with E. coli counts over 5,000 CFU per 100 milliliters, you know we have a serious problem. On the control floor, your biggest warning is going to be the SCADA system screaming a UV intensity low alarm, or seeing that intensity drop 20% or more below our baseline. Another huge warning, the UVT% dropping below 65%. Honestly, if the water gets too cloudy, that UV light is totally useless.
But brothers, you've also got to trust your own eyes and nose when you're out walking the floor. Check out the quartz sleeves. Are they cloudy, yellowed, or calcified? Look at the lamps themselves. If you're seeing blackened ends on the bulbs, that's cathode aging. Flickering bulbs or uneven dead zones, that points straight to a failing ballast or an exhausted lamp. And use your nose. If the effluent water still has that distinct microbial smell, or you see unbroken biological foam, the UV isn't working.
All right, part 4, our 7 root cause checks. It's time to start the investigation.
Check number 1. Cross-check your SCADA values against the design baselines to make sure the alarm is actually real. Check 2. Grab a calibrated handheld UV radiometer and compare it directly to the online sensor. If you're seeing more than a 15% difference, that online sensor is probably degraded by UV etching and needs to go. Check 3. Open up the logbook. Low-pressure lamps have a lifespan of 8,000 to 12,000 hours. And guys, don't forget this. At 8,000 hours, a lamp can lose 30 to 40% of its power, even if it still looks perfectly bright purple to you.
Check 4 is usually our most common culprit, the quartz sleeve. After you've safely applied lockout/tagout, get in there and inspect the sleeves. If you see chalky white scale, that's calcium carbonate. Green slime, algae biofilm. Reddish-brown buildup means iron or manganese. The bottom line is, if the sleeve is dirty, the UV light is physically blocked. It simply can't reach the water.
For check 5, test the water's UVT%. We absolutely need it over 70%. If it's too low, our upstream clarification is failing us. Check 6. Look at the actual flow rate.
If the flow exceeds our design capacity, the water is rushing by way too fast, which reduces our contact time below safety limits. Finally, check 7. Inspect the lamp's color during startup and check the ballast temperature. If that ballast housing is running over 60 degrees Celsius, or if you catch a whiff of burnt wiring, it's toast.
Section 5. Fixing and preventing. Let's talk about taking corrective action out there.
When things go wrong, you have a strict 2-hour emergency timeline. At minute 0, you confirm the violation, alert management, and immediately stop discharging to the river. Within 30 minutes, you've got to start diverting that treated water into our backup holding tanks. By hour 1, if the tanks are hitting capacity, you activate the backup chlorine system. Make sure we're maintaining a free chlorine residual of 0.5 to 1.0 milligrams per liter at discharge. And by hour 2, apply strict lockout/tagout procedures so we can safely get to work.
If you trace the problem to an expired lamp, here are the non-negotiable replacement rules. Number 1, lockout/tagout and UV safety glasses are a must. Number 2, you have to wear clean cotton or powder-free nitrile gloves. Seriously, never touch a new mercury bulb with your bare hands. The oils from your skin create localized hotspots that destroy the lamp's lifespan and can even shatter the glass. Number 3, box up the old lamps as hazardous mercury waste, never toss them in the regular trash. And number 4, once the new lamp is in, reset your operating hour counter back to 0.
Now sometimes the best fix is the cheapest one, just cleaning the quartz sleeve. Pull it out carefully and soak it in a 5 to 10% citric acid bath for 15 to 30 minutes to dissolve that calcium scale. Scrub it gently with a soft brush. Never ever use steel wool or anything sharp because scratching the quartz permanently ruins its transmittance. Rinse it down with deionized water so it dries without spots, and check very closely for hairline cracks. Even a tiny micro crack means you have to replace the sleeve or water will leak in and short out the lamp.
What if the lamps and sleeves are perfectly fine? Then you have to fix the process. Adjust your flow valves to bring the water volume back under the design max. If UVT clarity is poor, check on the upstream clarifier backwashing, or maybe add some powdered activated carbon to strip out dissolved organics. If it's an electrical gremlin, test the ballast output with a multimeter. Low-pressure lamps should read 60 to 120 volts AC. If it's overheating, swap it out. And don't forget to recalibrate your online UV monitor when you're done so your SCADA data is actually telling the truth.
Finally, Section 6, Monitoring and Lessons Learned. Let's make sure our fix actually holds up.
To prove to management and regulators that we are back in compliance, you need to monitor these exact parameters for the next 7 to 14 days. UV intensity has to be continuous to ensure it hits the design value. Calculate that UV dose weekly to make sure it's sitting nicely in that 20 to 40 millijoule pocket. Test inlet UVT percent twice a week, shooting for over 70%. And most crucially, pull lab samples for E. coli every single day. We need 7 straight days of clean results below legal limits before we consider this incident totally closed.
And to track all that, you'll be using the daily monitoring logbook. Brothers, I can't stress this enough. Meticulous documentation is just as important as turning a wrench out on the floor. I want to see the online UV intensity logged against the handheld readings, the flow rate, and the calculated dose on every single shift. If a state inspector walks into this plant tomorrow, this logbook is the only thing that proves we're managing our discharge safely.
So, what are the big takeaways from all this? First off, UV systems are definitely not an install and forget kind of deal. Keeping them effective is a constant balancing act between UVT clarity, calculated dose, and strict lamp life management. Second, never trust your eyes alone. Bulbs lose massive amounts of disinfection power even when they still look brightly lit. Third, garbage in means garbage out. Poor inlet water quality will completely ruin the effectiveness of a brand new bulb. And lastly, always have your backup chlorine plan primed and ready.
I'm going to leave you with one final critical warning. We are dealing with high-voltage ballasts and dangerous UVC radiation out there. Your life and your health always come before the equipment, no exceptions. Follow strict lockout/tagout procedures, wear your UV protective goggles, and use clean gloves. Equip yourselves with this knowledge, stay safe out there on the floor, and let's keep our discharge crystal clear. So, I have to ask, the next time those lights go dim on your shift, are you ready to handle Incident 23?